Okay, we're going to talk about frequency response. So far, in this class, no, not only in this class, in most of your classes, you are talking about time response. So what I mean is you are having output y equals to function in terms of time, right? When we put t over here, this is in terms of time. Normally we use seconds. And we have been talking about transient response and steady state response. So we do time over here, we do magnitude, and many other things on the y-axis. However, this is only one part of natural environment, because in many cases, the information included in our daily life, not only in terms of time, it's also including in terms of frequency. For instance, radio. So I'm not so sure you guys still listen to radio. So you have AM, FM, right? Amplitude modulated frequency. This is frequency modulated frequency. So when we have those kind of things, when we listen to the music, let's take this one as our response. No, use this one. So if you listen to the music, if you put time series, so use scope to visualize what's going on of the waveform of a song. It looks like this, right? But if you are using your radio, listen to it. What do we have? We have 90.9, 91 megahertz. You got 108 megahertz. All those signals, all those songs are existing in the air, simultaneous, at the same time. So when we have those musics, how does our radio device tell the difference between one song and another? Do you ever wonder why we can see over here? This is our carrier signal. So when we have our carrier signal over here, the signal is going to be attached on top of this. Okay? So when we have those kind of stuff, it is actually modulated. Okay? So this is plus 90 megahertz. And this is adding another frequency to this thing. So add them together, it becomes the signal our radio is actually receiving. So over here, if you use this signal minus 90.9 megahertz, minus 91 megahertz, anything faster than that, just build it out. Then you can get your waveform out of the signal received. Okay, so this is part of our system. Now go back to mechanical system. So you got the cantilever beam, and you put the force over here. What happened? It's going to vibrate. And if you visualize what's going on over here, you're going to see the magnitude like this, right? But if you have two forces, one hit over here and the other one hit over here, what happened? If you just put a force over here, it got one frequency. If you put a force over here, it get another frequency. Does it make sense? Because you put your force at different location, the cantilever is going to generate different frequency based on where you apply the force. That is something you can get a response based on your engineering mathematics force response, right? Now, if you add this one together, what you're going to see is something like this. And we're human beings. We get used to time response. But if we combine multiple frequencies all together, we do not recognize what's going on because this one is no longer periodic. If this one is 7 Hertz, 19 Hertz, this one is 37 Hertz, they are not close to each other, and you cannot find the common number of those two things together, so it becomes difficult to visualize what's going on. So when we have something like this, the signal becomes ugly, and we cannot recognize what's going on, even though this is a combination of two periodical signals. And it's going to be difficult for us to recognize what's going on. So when you are trying to understand the response of mechanical system, you need to think the signal in 3 dimensions. First is like what we have regularly. This is our time response. Okay. The second one is frequency. So you got 1 Hertz, let's say 1 radians per second, 10 radians per second, and you got 1 peak over here, another peak over here. Okay, so if you, this is frequency. So what does that mean? If you put this one, I'm telling you this is 10 radians per second, and this is like 2 radians per second. So if you put that back into time series, what do you actually have? You're going to see this one. This one is 10, so we got 10 times. Okay, so I should do something like this because this is something I have right now. So this one is, if you plot this one to time domain, it becomes something like this. If you plot this one, the second peak, to the time domain, it looks like this. So what I'm trying to say is, let's do it this way. If you try to visualize this one on this point, frequency and magnitude point, you see a peak. Okay, I'm pointing this one to the other direction, so it's smaller to bigger. So this is how we visualize of this point. If you visualize in this point, what do we have? That's not. This one over here is does it make sense? Now, we are human beings. We do not visualize things in this direction. We visualize things in this direction. So when we combine everything all together, what do we have? This is a summation of those two signals. So when you are trying to understand what frequency is going to look like, you need to think in 3 dimensions. This direction is how we visualize things. These things, if you use frequency analyze, you use Fourier transform or Laplace transform, you actually put everything into this direction. Combine everything all together, we visualize what's going on. So sometimes it's difficult for us to analyze what's going on in time series. But if we do Fourier transform, you can actually know what's going on in frequency domain. And you can just filter out everything. Is that clear? Everybody understand what I'm talking about? Okay. So frequency response is, the basic idea of frequency response is like this. Now, in order to get frequency response, we actually have a tool already. Laplace transform is converting everything from time into S. If we replace S with j omega, omega is radians per second, so we can convert signal from time domain into frequency domain. We already have that. So this topic over here is just tell us how are we going to generate the frequency response using a tool we already have. But before you start, I would like you guys to exactly understand what I'm talking about over here. How do we visualize time, frequency, and magnitude in those? How are we project everything all together? Okay. So frequency response to compensate for system dynamics. Not only time responses need to be taken into consideration, but also frequency responses. Linear systems respond to sine wave. So when we are talking about those kind of things, we are not discussing square wave, triangular wave. Every time we talk about periodical signal, we are talking about sine wave or cosine wave or sinusoidal wave. Okay? So every time we see that, it's a sine wave. Okay? So frequency responses, there are 2 things you need to remember. Frequency response is a function of omega. And this one included 2 things. One is magnitude. The other one is phase. Okay? So when we talking about frequency response, okay, let's do an endeavor. So if you use your hand, hold this thing, and move that slowly. So if you put 1 hertz, and you put 1 centimeter movement, the end over here is going to follow our movement 100% precisely. But if you use hammer, if you put an excitation over here and use 10 hertz, well, not here, over here. Vibration table over here. If this is 1 hertz, then this one is moving up and down slowly. But if you start to increase the speed over here, like, what do you observe? This one over here is going to fall behind. It becomes, when this one is moving up, this one is slower, right? If the speed over here becomes faster, if this one becomes faster and faster, what happens? You're going to see this one maybe 1 cycle behind. And if this one goes to maybe 1 kilohertz with small magnitude, you cannot see anything happening over here, right? So this kind of things tells us frequency response of a mechanical system. Typically, at low frequency, good response and small delay. High frequency, poor response and huge delay. When the frequency is low, the magnitude over here is going to be the same as this side. But if your frequency becomes higher and higher, the vibration here becomes smaller and smaller and smaller. And after a certain frequency, you cannot visualize what's going on over here, even though when you use the finger you can feel it, but you can no longer visualize that. The other thing is delay. What is a delay? Delay means, okay, this is my input signal. Here's my output. It's like this. I ask everything to start from 0 seconds, but the endpoint over here actually starts its movement after delay. This is called delay, and it's actually slower. But when we are talking about frequency response, we are not talking about delay. Sorry. Okay, so over here, when we are talking about a cycle, how do we define a cycle in terms of rotation? How do we define that? Pi or what? Right? So if I know my TD, how much the signal is being delayed, divided by total duration, that is going to be 2 pi over p. This one is called phase. Okay, so when we are talking about delay in frequency response, we are not talking about how much time, because again over here this is radians per second. Time does not mean anything in this on this point. We can only know the phase, because it doesn't matter what you do. You have 1 radians per second, 10 radians per second. One cycle is always 2